Good morning, everyone. If the online audience cannot see my screen, please let me know. Uh, Thank you so much for being here. Uh, and today, I'll be presenting my proposal defense on generalized planning using language models and its applications. Um, Huge thanks to my defense committee, which is comprised of Dr. Ramton Zand, who is the examination chair, and my co-advisors, Dr. Biplav Srivastava and Dr. Amit Sheth, and Dr. Leo Horesh from IBM Research, and Dr. Sharat Sridharan from Colorado State. So planning tasks are everywhere, but they're hard to scale. And whenever I want to introduce somebody to a planning domain, I like this excerpt from the Russell and Norvig AI Modern Approach book, which says many real world tasks can be framed as sequential decision making problems with goals, constraints, and actions. So, what do these domains look like? They can be as simple as cooking recipes, where we start off with ingredients and we have an end goal in mind, or a travel route where we start from probably our home today and reach the lab, and goal-oriented dialogues where conversation between an human and agent or between two humans is always reflected towards the goal, or procedural workflows like business processes and robotic manipulations. And these tasks come in diverse representations. They can be written in natural language, like cooking recipes, or they can be semi structured, like business processes or workflows, or they can be fully symbolic, which includes PDL domains. And structured planning, for example, strips based planning, is done via PDL, which is planning domain definition language. It is a Lisp-inspired programming language specifically written for defining, planning, or sequential decision-making tasks. And it is formally represented as a phi tuple, which consists of actions, preconditions, effects, goals, and the state transitions. Here I have a small hello world example or introduction to what planning is for somebody that is new to the domain. Let's consider two blocks A and B on a table, and there is a single robotic arm trying to manipulate these two blocks, and our initial state consists of A independently on table and B independently on table, and our goal state is to stack A on top of B, right? And a planning problem, when this is casted as a planning problem, the goal here is to come up with a sequence of actions that takes us from the initial state to the goal state, right? And these actions are formally defined as follows, where there is the name for an action, and there are preconditions, that is what is the state of the environment that is set is said to be true when I can perform this action. And when the action is performed, it brings in some addition and delete effects in the environment. Like for picking up a block by the robotic arm, the preconditions, that is, the environment should be having the block clear, that is, it should not be stacked in between two blocks, so I cannot pick it up directly. And the block should be on table, and the robotic arm should be empty. If it's already holding a particular block, it cannot hold another block, right? So when these preconditions are met, I can perform the action of pickup, that is, my robotic arm can go and pick the block up, and this brings change in the environment. Right now, my robotic arm is holding the block, and the delete effects that happen in the environment are the block is not clear anymore because it's already being held by the robotic arm, and the arm is not empty anymore because it's holding the block. This is a very formal way to define a planning problem. Now, uh, these planning problems written in PDL are solved using classical planners, right? They use search and heuristics to solve for plans either in a satisfying way, that is, they're not necessarily optimal, or a combination of search and heuristics can even give us optimal plans, that is, they're of the shortest length. But the adoption of classical planners basically suffer due to two main reasons. That is, they require manually engineered domain models. So the curse of domain definition is what hogs down structured planning or strips-based planning, and also a massive reliance on search algorithm and heuristics. That is, if I do wrong search, then I might be stuck in solving a particular problem. And if I use a wrong heuristic, that could act as misguidance, that would lead me away from the goal state. And if I tweak the domain without knowing all the other conditions that need to be satisfied, then everything just breaks. So automated planning is conceptually very powerful, but operationally very brittle. Its performance depends heavily on the domain models, the search algorithms, and also the heuristic design. So why even look at large language models or language models in general? Uh, and how can they overcome the three or the two major drawbacks of classical planning systems. So language models are basically derived from the transformer architecture, which consists of an encoder and a decoder stack. And the major component that is driving the transformer architecture is the self-attention mechanism. And language models have demonstrated that with scale, that is increasing the number of parameters, they become highly expert statistical learners of any given data. So they currently, when we interact with ChatGPT, that is trained or sort of learned a probabilistic estimation of the entire internet, it is able to answer most of our queries rather than us going back and doing a manual search and sifting and sieving through all the resultant search pages. So this is a very nice infographic that was released as part of Google's PaLM language model, where they scale from 8 billion parameters to 540 billion parameters, and they show the kind of tasks that are acquired by the language model as the scale increases, right? At 540 billion, we do a whole bunch of things. But essentially, language models come in three different architectures or language modeling architectures. What we know of ChatGPT that is very popular and widely used by everybody alike is only one piece of the puzzle of building a language model. So we'll just look at what are the different ways language models can be built.
The bubbles indicate.
The size of the bubbles are just, they do not indicate performance as such. It is just a representational figure. So the first language modeling architecture that kickstarted the whole journey into building large language models is encoder-only models. And the representative model that we know of in this class is Google BERT. And these models are specialized for representational learning. They're also called as masked language models because their pre-training objective is mask a certain word and try to predict it. With this simple pre-training objective, the goal here is that we get a better contextual representation for each word in the entire English vocabulary. And these models are excellent for classification tasks and semantic similarity and also information retrieval. The next class of models are decoder-only models, although these came at the very end. Um, so these models are specialized for coherent sentence generation, and these are the models that we widely interact with, be it OpenAI's ChatGPT, Meta's Llama, and these models work with only next word prediction, right? The pre-training objective here is to predict the next word, given a whole sequence of historical tokens, right? And here in our example, we can see how this works. If a sentence like the dog chased a, and we want to predict the next word, the model comes up with a probabilistic estimation on the vocabulary that it has as to what the most probable next word is. And the third category, which actually came after encoder-only models, are encoder-decoder models or sequence-to-sequence models. And these are designed for input-to-output structure transformation. They're excellent for machine translation tasks and summarization. And one representative model of this is Google T5, which later was scaled to call as Plant T5, which consists of almost a couple of billion parameters. Now, operationalizing the generalized planning definition for this defense, most planning domains do not present a single problem. They actually present a distribution of related problem instances. For example, in blocks world, where we saw an example, if I stack A on B as my simple unit action, but I want to perform this action in a wider uh, initial state to goal state transformation, I already know how to stack A on top of B, right? And when it comes to cooking recipes, if I know how to make pasta, I already know how to boil pasta al dente, and I know how to chop onions, right? So I do not acquire those skills from the beginning again. And be it in travel routes, if I have a travel itinerary, I already know how to go to a bus stop if I do it repeatedly, and I that becomes a part of navigation skill that I acquire, and I do not revisit Google Maps or take help of anymore. So a scalable planning system or a generalizable planning system must therefore avoid solving each instance from scratch and instead extract reusable structures from prior experience. So for this proposal defense, I wanted to give an operational definition for generalized planning, where the goal is to transfer from small to large instances, that is, learn patterns from smaller instances of a domain and apply them directly to a larger, combinatorially harder problem. And reuse prior solutions and experience. So maintain a library of solved problems and derive heuristics or partial plans from them, and use this accumulated experience to reduce search or even bias the exploration strategy. This technically mirrors how humans reuse strategies rather than starting each plan from scratch. And the final uh, point that I want to achieve in generalized planning is operate across heterogeneous planning like tasks, that is move beyond classical PDL where there is a structured definition and go to semi-structured or even natural language planning tasks, which involve cooking instructions, travel routes, workflows, and goal-oriented dialogues. All these share a common structure. That is, they have states, they have actions, and they have goal-directed transactions, even if expressed in very different modalities. So the objective here is to build planners that generalize by learning structure from small instances, reusing experience, and operating across diverse planning tasks, rather than resolving every problem from scratch, which is currently what happens in a planning system. And presenting the dissertation proposal statement, this dissertation investigates how language models can be developed into generalizable planning systems. I basically study how language models are currently used in automated planning and how they can be adapted or trained to generate valid and coherent plans, how neurosymbolic methods can integrate language models with symbolic reasoning to improve correctness and robustness, and how generalizable planners perform when applied to real-world domains such as information retrieval and manufacturing replanning. I would address four research questions as part of my proposal defense, and these are bucketed into four different categories. The first is characterization, where I talk about how language models are being used in automated planning, and then move on to specialization, that is how language models can be effectively used for plan generation. And there are three sub questions that I answer as part of specialization. That is, how well do pre-trained language models perform on plan generation tasks? Does fine-tuning pre-trained language models or using any model adaptation techniques prove effective for improving the plan generation capabilities? And how can a compact language model be trained from scratch to better support plan generation? And the third category is integration. That is, how can language models be used along with symbolic methods to achieve robust plan generation via neurosymbolic architectures? And the fourth is application, where we'll see how generalized planners perform in collaborative assistance for information retrieval and in manufacturing domain for replanning. Um, and the whole presentation is divided into two parts, where first, in the first part, I would cover the foundational work, and this addresses all four of the categories, but some of the RQs are missing, which I'll address in the ongoing work. So moving on to the first research question on characterization, that is how are language models being used in automated planning. And we wanted to understand how in the existing literature, how LLMs are being used for planning. And there is an explosion of research papers in the space of language models and planning, starting with 2022 when we started our exploration of collecting research papers. There is almost 850% growth that we saw when we moved to 2023 in the number of research papers that came out in the space of LLMs and planning. And there is no unified taxonomy that we consistently observe, and also unclear boundaries on what counts as planning when language models are involved.
So not done the taxonomy.
We did. That's the contribution of this work. All right. So we conducted a search which spanned across multiple academic databases, steered by a huge keyword set, which included keywords like LLMs in planning, large language model splits, automated planning, LLMs in robotics. And we identified a total of 126 papers after a lot of post-processing where we removed reduplicates and um, removed some papers which did not have succinct contributions. And this survey was conducted this survey ended on November 2023. And once we had the 126 papers, we did manual categorization of the 126 papers and segregated them into 8 categories after reading each paper and coming up with a category on the fly. So we did not predetermine the 8 categories, but these categories were built based on going manually through all the papers. And here, the constraints we followed was that each paper could belong to multiple categories, and the categorization was conducted based on the sole purpose of the application of LLMs in planning. As a result, the 8 categories that we obtained are language translation, plan generation, model construction, multi-agent planning, interactive planning, heuristics optimization, tool integration, and brain-inspired planning, which I'll define in a little bit. But we also have a interactive tool that people can go and see all the papers that fall under the category of LLMs and planning, and across all the categories that have come about by clicking on each category across over the period of time. And so going to the definition of all the 8 categories that we manually have defined, in language translation, large language models are essentially used to convert English sentences into structured representations, strips-based structured representations like PDL. And in plan generation, language models are given the whole uh, otherworldly task of generating the sequence of actions and expecting them to be valid. And in model construction, language models are basically prompted to use their parametric knowledge and create an entire action space for a certain task. In multi-agent planning, different smaller LLMs are used to coordinate with each other to solve a planning task. And in interactive planning, all the techniques such as reprompting LLM or doing self-reflection kind of things fall into place for plan generation. And in heuristics optimization, language models are basically used as heuristic generators, and in turn, the heuristic is used with search algorithm like MCTS or A star in order to generate a plan. And in tool integration, language models act as orchestrators to coordinate with a bunch of planners. And in brain inspired planning, new architectures that basically are inspired from the cognitive approaches are designed to solve plan generation. And these are the papers that fell into each category. And we can clearly see that plan generation has the most number of research works associated with it. And in my proposal defense, I'll be talking about plan generation and also multi-agent planning. When we did the manual literature uh, categorization, the immediate next step for us was to automate this process, right? Because it is hard to keep up with the amount of research papers that is coming in the domain. So the immediate next question that I asked was, how do we automate the static literature selection and categorization for this rapidly growing domain? For this, we came up with a framework where we systematically collect papers based on the same keyword vocabulary that we have to obtain papers. And then we use the previous 126 papers and associated categories obtained from human experts as the training data to train an automated classification uh, model, and use that to label the new set of papers that are being extracted, right? And when there is no label associated, or a label is associated with less probability, then we pass it on to a human expert who can manually correct the labels or reassign the labels if the category is missing or if a new category has come up, right? And all of this is added back to the visualization tool that I initially showed. And in D1, as I was mentioning, we had the 126 papers that were coming from up to November 2023 literature that was selected. And in D2, we had 47 papers between December 2023 and September 2024. And we created 5 different classifiers. And the best performing was, of course, like the human augmented one. But if we only look at the classifiers, then on the new data set, SVM was performing the best. And to plot how the shift or the category drift has happened from the original manual classification to the automated classification, we see that plan generation continues to be the domain where most contributions happen. But also 2 new categories have shown up when we did uh, a rerun of the paper selection, that is goal decomposition and replanning. And this is the overview of the tool where one can interact with the categories and look at all the papers across the temporal timeline. Moving on to the second research question, which is on specialization. That is, how can language models be used for effective plan generation? Uh, I would like to address the first sub-research question in this segment, which is how well do pre-trained language models perform on plan generation tasks? So the pre-trained language models, to sort of define them, are large neural models that learn broad linguistic features, semantic features, and world knowledge by training on vast data sets with self-supervised objectives, like the learning that I was talking about for encoder-only models or next word prediction for decoder-only models. And evaluating pre-trained models clarifies their capabilities, limitations, and also if there is a need for further specialization for a given domain. So there is a very seminal piece of research in this space, which was titled LLMs can't plan, and this was benchmarked on Plan Bench. And the authors take three domains, which are classical planning domains, blocks world, which I briefly introduced, and logistics. And there is a mystery blocks world where there is randomization in the action names and object names, right? And we are concerned with the zero-shot performance because that is how we truly can evaluate the pre-trained model capabilities. And all of them perform, like if we look at GPT-4 and GPT 3.5, the best performance is at clocked at 17%. So all of them have sub planning capabilities. That is what we are starting off with. Although there is an existing work, but there are three primary language modeling architectures that I introduced, and most prior work evaluated only decoder-only models, right? Because the popularity and the ease of evaluating them, and also the widespread utility for decoder-only models, and also this evaluation relied only on uh, prompt engineering of methods, more or less, for generating plans from textual representations. So as part of trying to understand how language models are being used selectively for plan generation, um, we again looked at the literature and we came up with three different categories where language models are directly used as planners, or language models are used in tandem with planners, and they are used as part of cognitive architecture where there are different interplay between different language models, right? And in language models as planners, most of the work falls in decoder-only architectures, and encoder-decoder is one work that we did, and encoder-only is one only a single work that existed in encoder-only architectures because encoder-only architectures do not generate text as such. They give a certain heuristic. So using them directly for plan generation is not intuitive out of the bat. Absolutely. Mm-hmm.
I think they're not necessarily a negative point. Is that right? So like the fact that there are decoder only models,
Mm-hmm.
they rely on prompt engineering. Is that the message you're giving, or you didn't? You just is an observation.
So it's not a negative point. It's just that there is a much more elaborate study that could be performed here. We can also look at fine tuning because prompting is one model adaptation approach, which also coincides with fine tuning, which is another model adaptation approach, right? So I think the comparison should be spread across the possibilities, and then a certain methodology or adaptation technique should be chosen. So that's what I'll try to get into in the rest of the slides. Yeah, right. So and like piggybacking on the question, the need to evaluate pre-trained language models across input representation, that is text, PDL, and also we came up with some representation called as compact, which is semi-structured of sorts, and also across language modeling architectures, where three of them that were mentioned earlier, and the complexity of planning domains. Although the complexity does not have an immediate effect, I mean, language models do not care about the complexity of the input, but it is interesting to see how well the performance improves or drops based on the complexity of the domains. So we built our own benchmark data set, which consisted of six different planning domains, and each of them had 3,600 different test cases or test problems per domain. And we classified each domain into easy, medium, hard. This is the difficulty classification is based on the total number of evaluated and generated states when used with A-star search. And regarding the input representation, if we take a Bloxwell problem, these are three different input representations that exist for the same Bloxwell problem. The natural language is very verbose, and on here we have PDL, which is having a structure. Then we have the compact form, which is something that we came up with, where only specific parts of the PDL are obtained, like the goal state, the init state, and the action with preconditions and effects. And we used these different baseline models. We have a total of six baseline models, two per the category or the language modeling architecture. In decoder only, we had GPT-4 and we had Code DaVinci 03, which is a code specific model. And in encoder decoder, we had T5 and Code T5, which is a code specific model. And in encoder only, we had BERT base and star encoder. Star encoder is the code specific model. So here the understanding is to look at all the language modeling architectures and also look at the different pre-training data that went to train the model, whether it is general purpose or whether it is code specific. Right. And oh, our results show subpar performance. So language models out of the box when they're pre-trained and zero shot model adaptation perform very poor when tested on plan generation tasks. And the best that we saw was Code DaVinci 03 on PDL, which is again Lisp-inspired programming language. And the amount of satisficing plans that we got were 17.42%. So this rose the question, does fine tuning improve plan generation, right? So we post plan generation as a machine translation task, and that's how we look at it. So in machine translation, there is an encoder that basically is generating a mathematical representation or a vector for an input, and the decoder is auto-regressively generating the target output. So something similar is what we adopt for plan generation as well, where we take the compact form, pass it through an encoder, and we obtain the mathematical representation, use the decoder to generate the plan. So the training architecture for the fine tuning looks like this, where the training data consists of 14,400 plans per domain, and we have 6 domains. And the test data is the 3,600 test problems that we had per domain. And we use Code T5 as the fine tuning model based on our definition of plan generation as a machine translation task, and from the previous understanding that code specific models have a better performance, right? And what the fine tuned model is called as Plansformer here, and Plansformer is deployed as a tool where one can upload input in PDL and use Plansformer to generate a plan. Let me quickly show how that works. So we can load the domain file, the problem file, just like how input is given to a traditional planning system. And we can also validate the generated plan, because when using a learning based planner, it's not guaranteed that the output is always correct. So this is how the output from Plansformer looked like. So now we wanted to do a more detailed study on whether fine tuning uh, or how fine tuning fares up against other model adaptation techniques. And there are two primary model adaptation techniques. One is fine tuning and the other is prompting. And fine tuning is a method where we update the parameters of language model using a labeled data set for the target task. And prompting is a method that modifies the input of an LLM using a template or a queue to elicit the desired output. So here is our detailed evaluation across the language modeling architectures, across the three input representations, that is compact natural language PDL, and across 3 different model adaptation techniques: zero shot, one shot, chain of thought, for prompting and fine tuning where possible. And the best performance we see is with Code T5 when fine tuned on compact data. And we see on the easy domain, we see 97.57% of satisfying plans. So satisfying plans are not optimal plans, but they are valid plans. And on medium, we have 92%, and on hard, we have 89%, which is the best performing results that we see across all the language modeling architectures. So the next best was with one-shot prompting of Code DaVinci 03 with PDL representation. But that is 54% lesser than what Plansformer has showed for the easy domain for satisfying plans. Although the plans uh, can be invalid, which is not a desired case for planning community as a whole, right? So planning is always sound and complete to begin with. So we got to the question, like, what is even the purpose of creating these models where they have 80 to 90% performance? How can we use that, right? So if we look at and then we try to qualitatively understand the generations from LLMs. This is from 45, which was fine-tuned on planning data. These are invalid plans. But if we can see the comparison of the actual plan with the generated plan, there is a subsequence of the generated plan which is valid. And then it starts to drift off and generate nonsensical actions which do not make sense or which violate the constraints that were initially set forth, right? So the whole question is, can we use this subsequence of actions that are actually valid and use that as a heuristic with a traditional planner to improve plan generation instead of doing planning from scratch, right? In that way, we can cut down time, we can cut down the memory that is being consumed, and we can also avoid the huge branching factor that the traditional planners can run into. This is what I'll address in the next research question, but I'm leaving with this particular interesting observation that we saw with fine-tuning language model. So post fine-tuning, we also wanted to ask the question, do these model adaptation techniques, be it fine-tuning or prompting, help in generalization, right? And we define three sets of generalization that we wanted to evaluate. The first is plan length generalization. That is, we train on a set of uh, plan lengths, and then we evaluate it on plan lengths that fall out of this training distribution. The other is object name randomization, because in planning, the object names or the action names do not hold any semantics as such. Like pickup is just for our understanding, it's just like any variable in a code, right? It's just meant to be understood. But pickup, if changed to, let's say, put down, it should ideally still generate the same plan. But when these are given as input to language models, they get confused because they are trained in a completely different way to understand words differently, right? And the third is unseen domain generalization, which is probably the most interesting, or what we want the model adaptation techniques to do. That is, we show examples from a certain domain, but we want the model to be able to generate plans for a completely different and maybe complex domain, right? So I'll go through each of the tasks one after the other. The first is plan length generalization. So we test on 10 different plans that fall out of the training distribution. The grayed out part is the training distribution for the easy, medium, and hard domains. And we see that the fine-tuned model is able to perform a little better than uh, than the prompted code Da Vinci. The star marks show the prompted model performance, which is almost clocked at 0 degree of correctness. But the fine-tuned model shows some degree of correctness that is scattered between 0 and 1. And when it comes to object name randomization, prompting approaches are not affected by the object name randomization. And we test with 3 different variants, where each variant corresponds to using either alphanumeric or string with 3 or random numbers. And the fine-tuned code T5 always suffers the most when the object names are randomized and the performance drops. This probably can also be accounted to overfitting on the training distribution, the object names in the training distribution. So techniques like using random object names during training, which is something that we have not done, might improve performance. But as it stands, the fine-tuned code T5 showed the most degradation. But when we use a symbol table, that is, map the randomized object name to the original training distribution and then pass it as input, then we recover performance. Whereas Code Da Vinci is not affected, it uses the same object names that is given as part of the input, even if randomized or unrandomized. But the problem is it has no planning capabilities out of the box. And the third is unseen domain generalization, where both the models collapse. They technically uh, do not generate the prompting with Code Da Vinci does not generate a valid plan, whereas fine-tuned Code T5, when prompted a completely new domain, which here is logistics, um, it generates actions that are very close to what it has seen during the training distribution, but these actions are not even present in the new domain that we are being asked, that we are giving as input during inference. And moving on to the third research question, where we'll talk about how language models can be used along with symbolic methods to achieve robust plan generation via neurosymbolic architectures. For this, I want to give a brief introduction of how human cognition works. And this is uh, inspired from the thinking fast and slow paradigm given by Daniel Kahneman, where there is system one and system two. A human brain operates in 2 different systems. System one is fast, it is unconscious, and it is automatic. Let's say if I hold a very hot object, my immediate action would be to redact it, but not a reason about whether I should redact it or not. So that is a system one thinking. When we move to the system two, it is slow, deliberative in nature. It takes time, but it often arrives at a correct answer. This is more like if I have to invest in a stock market and if I want to see some returns, I would rather look at all the historical performance and then choose very consciously what I want to invest in. So system one can perform cognitively easy tasks, where system two handles more complex tasks, and system two's search for solutions is usually supported by system one's heuristics. And there is some skill learning that happens. That is, some tasks, when repeatedly done, move from system two to system one. Like addition, when I was in first grade, probably I took a lot of time to do addition and I used fingers, but when I came to third grade, it has become a simple task, right? And there is cognitive control. That is, system one is reactive, and sometimes system two may override it based on the actual requirements of the task. So how can this be converted to an AI system? Uh, So system one solvers, if we translate what we saw for cognition in humans, system one solver in AI basically relies on past experience. That is technically what we did with Transformer, created a data set of plans and then trained, fine-tuned it. Whereas system two solver relies on procedures. That's what a classical planning system does, takes a new planning instance and actually branches out all the possibilities and chooses a path. That is a sequence of actions that solves my planning problem. System one is reactive to new problems. It does not think much. It produces an output. The output might be incorrect. Whereas system two is called by metacognition. That is, if the system one's performance is not up to the mark, that's when system two is invoked. And system one generates solutions with a certain confidence, and system two always generates correct solutions. And system one are complexity independent, and system two solvers are complexity dependent. That is, it might take more space, more time, based on the input complexity. And I also mentioned metacognition. So the role of metacognition is to monitor and control cognitive activities. That is the system one and system two invocation that is happening here. And the main goal of metacognition is to improve the overall system's decision quality. And the choice that we went with metacognition here is a centralized metacognitive agent that exploits both internal and external information and arbitrates between system one and system two as needed. So this is the SOFI architecture from a developer's point of view. So system one, system two are solvers, right? So there is a base solver class that needs to be implemented, which comes with functions like correctness, confidence, the solution, and the running time. And system one solver basically inherits from the solver. It inherits the solve function and the calculate correctness. And the system two solver has solve, estimate difficulty, and also calculate correctness. So when a new problem instance is encountered, it is always passed on to system one. System one produces a solution along with the correctness for the solution. The correctness is then obtained by the metacognition with a set of parameters like context, threshold, and prior experience, where metacognition evaluates whether the system one solution should be directly passed as output or whether it needs system two's help to generate a better solution. And that's when system two is invoked. And system two looks at estimates the difficulty of the problem and then solves that particular problem if there is enough time for the system to solve. So how do we adapt the SOFI architecture that we previously saw for the task of plan generation? So here we mod the system one with Transformer, and that is obtained by comparison across a wide range of possible system ones, where we have a random baseline. We use a case-based library with Levenstein distance, Jacquard distance, and we also use a mix of different approaches like Levenstein and Jacquard and Transformer, and we see Transformer as the best performance on the tested 500 problems. So system one is um, basically Transformer, as that is the best performing combination that we have here. And system two is two classical planning systems. The first is fast downward for plan generation from scratch. That is, we do not use any generation from Transformer as a heuristic or a bias for fast downward. And LPG, which is based on local search, this is for partial plan completion. That is, if we see the system one generation, that is Transformer's output, to have some degree of correctness between a certain range that is preset, then LPG is used along with the system one or Transformer's plan to replan faster. And metacognition module is a rule-based function that chooses when to adopt S1 or S2 based on previous experience, expected cost, and the expected accuracy on similar problems that were encountered previously. We have three algorithms, which I already kind of defined. We can come back to this if there are more questions. All right. So the results for the plan SOFI, which is based on the SOFI architecture for plan generation. On the columns, I'll just quickly explain what the columns mean. So FD is fast downward, which is our classical planning baseline. LPG is based on local search, another classical planning system as a baseline. PF is transformer. Then on the last four, we have different SOFI combinations where we have transformer with fast downward, where we have and next we have transformer with LPG, and then we have transformer with fast downward and LPG. Fast downward and LPG are invoked based on certain degree of correctness conditions of the output from transformer. And then we have transformer with LPG and LPG, where one version of LPG is used for replanning as well as LPG is used for planning from scratch. So we see that FD has the best optimality. So optimality is given here, but it has a high overall resource usage where time is measured. It takes 8.5 seconds to solve all the 500 planning problems that is part of our test set. And LPG is the most efficient. It solves all of the planning problems, 500 of them. But the optimality suffers the most when LPG is used. But the time it consumes is way lesser. Right, and Transformer solves less problems if we only look at Transformer and not in SOFI. Transformer being used in SOFI. So Transformer alone solves 80% of the test set, uh, which is way lesser than fast downward and LPG. But many of these plans are optimal because the training data that we use for Transformer is built with A-star search and landmark cut heuristics, and it takes almost constant time to solve any plan. So among the SOFA instances, we can see that it provides multiple choices. So SOFA with Transformer as system one and fast downward and LPG as system two represents the most balanced trade-off among all the combinations that were tried out. It solves 490 of the problems with 2.2 seconds and only a 1.13% loss in optimality. Whereas SOFI with Transformer and LPG is best in terms of the number of problems solved, if that is the priority and not the time taken to solve the problems. And SOFI tool, so absolutely. Mhm. So the way we do optimal plans calculation here is by generating a ground truth using A-star search and landmark cut heuristics. So for classical planning problems that have unit cost associated with each action, the usage of landmark cut heuristics with A-star provides an optimal plan. But there is a small caveat here. That is only one optimal plan that we obtain as part of this process, although there are many k optimal plans possible, which we do not consider in this setup. So we are only comparing against that one ground truth optimal plan that we have generated. Yes, that is when we count. Right. No, no. Yeah.
500. The difference is the 500 of LPG and the SOFI from an LPG. Both of them have plans.
Mhm.
And the SOFI plus transformer and LPG gives you 434 exact optimal time to get that.
Right. Okay. So SOFI tool is released as open source contribution, and there is another version of the SOFI architecture which basically is fit or catered towards using language models specifically. And in the previous architecture, we see that the system one or the transformer is only called once, but with techniques like self-reflection, prompting with feedback. These are not part of the the SOFI first version of the architecture. So the second version of the architecture uh, does incorporates all of this and is used in domains like constraint satisfaction, programming code generation, grid navigation, and disk-aware dialogues. So moving on to the final research question, that is how do these generalized planners created with language models and symbolic approaches perform in applications? The first is in collaborative assistance for information retrieval. So if most of us have interacted with Siri, and if we ask it to call a certain contact, some of the times it is unable to retrieve that contact and it just gives up. or it says, I don't see this specific contact card in your contact list, or sometimes even this. Uh, so conflict resolution, that is when there are multiple instances or multiple entries for a certain contact in collaborative information retrieval systems, is modeled as a planning problem in this work, allowing the resulting policies to generalize across varying databases and also data sources. So we created information retrieval system called as Prudent, which is built on top of Meta's Parlay core, and it is an RL-based system. It consists of planning, reinforcement learning, and language models at the core of it, where language models are used for intent understanding, reinforcement learning for scaling across or learning the taxonomy of the data sources, and planning to actually uh, act as a search guidance on how to break down a query into substeps and then retrieve information from the selected data source. So this is the overall state transition that the planner works with, and given the intent that is gleaned, uh, certain parts of the state transition are triggered. So we test with two data sets. One is UNSPC, UNSPSC, which is basically a repository of different tools that are present. And the other is ICD-10, which consists of different diseases that are mentioned. So we have three different outputs, only planning, where we have to the user has to manually choose the data source. And then conflict resolution happens based on the generated plan. And in reinforcement learning, the data source is automatically selected but takes more time. Whereas in planning plus reinforcement learning, the data source is automatically selected, and the planner actually helps in conflict resolution between multiple entities that exist that have the same keyword. Like if I want to query for players. And overall, these are the different combinations that we tested. PP is only planning, PRL is only reinforcement learning, and P plus RL is planning and reinforcement learning combined, which sees the most number of successful queries with the least possible time that is taken. So these are all the completed works, and the plan to completion from proposal to dissertation. If I go back to the research questions and highlight what is missing, are the research question 2.3, that is how can a compact language model be trained from scratch, and 4.2, which is manufacturing for replanning. And if we move on to how can a compact language model be trained from scratch, from the lessons that RQ2 has given us regarding the kind of input representation, the kind of drawbacks that language models have with respect to the generalization specifically that were identified, uh, we came to the main question or juxtaposition whether to understand is next word prediction in decoder only language models enough for learning to generate plans. So we are currently exploring new pre-training objectives that learn data flow and control flow, which is essential for plan generation. And scaling language models did not prove to be the solution, especially for the task of plan generation. So can we have a compact language model? Because planning is usually used on resource constrained devices, right? So a compact model that is trained solely for planning domains is what we want, instead of having a lot of capabilities within a single model. And many complex real world planning domains that we have identified, and some of them which we have talked as examples. So we wanted to incorporate all of that, move beyond classical PDL, but also have uh, a foundation model that can tackle design diagrams, dialogues, plans, recipes, and travel routes alike. And moving on to the other remaining research question, which is currently an ongoing effort, is generalized planners in manufacturing for replanning. So we are working in collaboration with Next Year, where the goal is to assemble a toy rocket which consists of 4 different parts: a nose, a tail, and 2 mid body parts. And ideally, if a rocket tail, the input is to place a rocket tail on the conveyor belt for assembly. This is the ideal working scenario, but an error can happen where the nose is actually picked up by the gripper, robotic gripper. So how do we overcome, instead of uh, overcome this particular erroneous action, instead of having a human reset the entire process, is something that I'm currently looking at, where I'm in collaboration, I'm training heuristic for action selection and using A star for actually generating plans that do replanning from the erroneous current state. And the timeline for completing RQ 2.3 and 4.2, which are estimated to be between December 2025 to March 2026. Much of the work is currently ongoing. So a bunch of experiments and getting the results is what is remaining. And May 2026, the final dissertation defense. And so the impact so far is I have around 1,000 citations with 41 research publications, 4 industry internships, uh, most of them thanks to Lear, 6 patents, 2 labs, and I was lucky to be the founding student committee member for AAA. Here it is me at IBM with Dr. Rao, who whose team has worked on the LLM's can't plan paper. This is our Plansformer work as a lab presented by Dr. Srivastava at AAA, which had a very good attendance. This is our whole group at. Sorry? Oh yeah, I was denied visa. This is our whole group at AAA 25.
Yeah, oh, that's
Yeah. This is Dr. Srivastava and me with Louis Lam. And this is another photo from the SOFI tool work, or I think Plansformer at AAA. Yep. These are the selected publications and patents. And if there are any questions, I can take them now. This basically concludes my presentation.
Just when you have any questions to be here, we have a few minutes for audience questions. Online students as well, or anyone who has a general question online or in person. Don't have anything here? Any questions from online folks?
I just want to make a comment. I think that the overall impact that Vishal has delivered is quite exceptional for a PhD student, right? I've been examining students for almost 2 decades now. This is quite remarkable. So well done, Vishal, for all of that work.
Appreciate it so much, Leo. Thank you.
Can have the public part of the questions by the committee if there's no questions. And then we will have a private part as well, which you can still stay and ask further questions if they need to.
Right.
But I don't know how many of the committee members are on the two on the side.
Yes.
And you go.
Yeah.
Perfect. So maybe we can start with you guys if you have any questions, and then we move to the in-person or vice versa.
this is the public part or this is the confidential part?
It's a public part of that, the questions that students and others can also benefit from. So if there are any questions that we and other audience here can benefit.
If it's okay, can I keep my discussion in the closed part?
Sure, absolutely.
So if there are no other questions, right, guys, you can take some snacks and then probably head out. We'll just take a few minutes break, and Vishal, if you want, you can also have something, and then we'll come.
That is so great.
Okay. So a few minutes, just a
Yeah.
couple of minutes.
Thank you so much, everyone, for joining.